Let's have a look at the concept conditional expectation and conditional variance. So before you watch this lecture, make sure that you have a decent understanding of normal expectations and normal variances. So to introduce this concept, let's say I have a random variable y, which is the yearly income, say, of a randomly selected individual in Sweden. So we have a population, we draw one individual at random, and we measure that individual's income. The expected value of y will then be equal to the average income in the population. So this will be the average income of the population. That's the expected value. Let's introduce one more random variable. X is number of years in school. So let's say if X is 12, that individual has finished high school. 5 years at the university, then X would be 17, and so on. So let's look at this concept. Expected value of y given, this vertical bar is pronounced as given or conditionally on. X is equal to 17. What would this be? Well, this thing here was the average income of the population. This thing you can think of as the average income of those with 17 years of schooling. That's the conditioning part. That is, we're conditioning on x equal to 17, just focusing on those individuals where the outcome of the x variable is 17. Now you would probably expect this expected value, this conditional expectation, to be greater than the expected value of y, as the expected of y contains the entire population. Similarly, the expected value of y given x equal to 9 would be the average income of those with 9 years of schooling, and you might expect that to be smaller than the expected value of y. So notice the difference. The expected value of y, that is, you can think of that as the average of the entire population, if it's possible to have a population concept in your mind. While this one is the expected value of y given that another random variable takes on a particular value. And the outcome of this second random variable x may very well change the expected value of y. Here's another example. Let's say now that y is the unemployment rate, then the expected value of y and the expected value of y, expected value of unemployment rate, given that inflation is at a certain level, answers two different questions. So this one answers the question, what's the expected level of unemployment if we have this particular level of inflation? While this one, sometimes that's called the unconditional expectation because we're not conditioning on anything, asks the same question but without an assumed level of inflation. In some cases, they can actually be the same. So here's a third example. Let's say that y is the outcome of tossing a die. So the expected value of y is then 3.5 right in the middle if this is a fair die. While the expected value of y conditionally on x being what you had for dinner, x equal to 1 if you had meatballs, for example, will be the same. The fact that you had meatballs for dinner doesn't affect the expected value of the die at all. So since these two are independent random variables, this will be the same. So let's have a look at this. We have two random variables. Conditional expectation and variance require at least two. So x and y are two random variables. Then this is the notation for the expected value of y conditionally on x. And in this case, I haven't specified a particular value of x. So that's called the conditional expectation. And the conditional variance is denoted using similar symbols. So the variance of y given x is the variance of the random variable y, given that I have a specific value for another random variable x. So let's look at an example which I think may illustrate these conditional expectations and variances. So let's say I toss two dice, and I'm going to let y1 be the outcome of the first and y2 be the outcome of the second, and I'm going to let x be the sum. So the unconditional expectation of y1 is 3.5. 3.5. If you don't tell me any information about the sum or anything like that, then that's my expected value. However, the expected value of y1 conditionally on x is an entirely different concept. That's the expected value of y1 if you know the value of x. And that's certainly going to change the expected value of y1. For example, if I tell you that x is 2, the sum of y1 and y2 is 2, what would your expected value of y1 be in that case? Well, if you know that x is 2, you know that what happened was that both y1 and y2 came out to be 1. That's the only way that the sum can come out to be 2. So in this case, the expected value of y1 conditionally on x equal to 2 is the expected value of y1 given that I know that the sum is 2. And for this particular case, just remind you of what these variables are. If x is 2, it must be the case that y1 is 1, as y2 must be 1 as well. So then the expected value of y1 is 1. y1 is 1 with certainty, so 1 times 1 is 1. In the same kind of with the same kind of logic, you can easily see that the expected value of y1 given that x is equal to 12 must be 6. If I tell you that the sum of the two dice was 12, well then you know that both of them came out to be 6. So the expected value of y1 is 6 in that case. So you can clearly see how the expected value of y1 depends on the value that you condition on. And for a slightly more difficult example, let's say that we want to look at the expected value of y1 given that x is equal to 3. Well, if x is 3, you know that the sum is 3. One out of two possible things must have happened. Either the first die turned out to show a 1 and the second one came out a 2, or the opposite happened. The first one came out a 2 and the second one came out a 1. These two are equally likely. There's a 50-50 chance of these two events happening. And that means that the conditional expectation of y1 in this case must be precisely 1.5. 50% 1, 50% 2, and and the expected value of y1 given x equal to 3 comes out to be 1.5. So the final thing I want you to notice with this example is that the expected value of y1 conditionally on x taking a particular value must be a number. But the conditional expectation of y given x, if I do not specify what x is, must be a random variable. This capital X can take values between 2 and 12, and I don't know which value it will take until I perform the experiment. I do have the expected value of y1 given x equal to 2, and I can calculate it for 3, 4, 5, and so on. So the expected value of y given x is a random variable which takes the value, for example, 1 when x is equal to 2. The probability of that is 1 over 36, and so on. So you need to think about the expected value of y given x if x is observed, that is x is equal to small x as a number, while before we know x, we don't know which number we will condition on, so then you need to think about it as a random variable. One important property of conditional expectations is the following. If x and y are independent random variables, then conditioning makes no difference. If they have nothing to do with each other, then the expected value of y given x will be the same as the expected value of y. So if x and y are independent random variable, then the expected value of y given x is the same as the expected value of y without conditioning on x. It's quite natural because they're independent, so x doesn't tell you anything about y. So the expected value of y will not change with this information about the value of x. And the same goes for the variance. The variance of y given x is the same as the variance of y if they are independent. We have these two really important formulas for the linear function of expected value and the for the expected value of a linear function and the variance of a linear function. Well, fortunately, they will hold also for conditional expected values and variances. So if x and y are random variables, a and b are constant, so we create linear functions here, then the expected value of a plus by given x is the same as a plus b times expected value of y given x. So I can still move the conditional expectations operator inside the parentheses. For the variance, we just remember that the constant a goes away and we need to square the b, so we get the variance of a plus by given x is b squared variance of y given x. Let's consider one example where we will actually calculate expected values, conditional expected values, and see how they are related to the covariance. So in this example, x can take the value minus 1 and 1. So I want to calculate here the expected value of y given x, and I want to do that for these two possible values that x can take. So I want to do it for x equal to minus 1, and I want to do it for x is equal to plus 1. In this cell, I am trying to calculate the expected value of y when x is minus 1. Well, if x is minus 1, I know that one of these two must be the outcome. So y can take the value minus 1 and 1, but I can't just simply multiply by these probabilities because they do not add up to 1. So to find the expected value of y when x is equal to minus 1, what I do is I take the value that y takes, minus 1, I multiply it by this probability, and I divide by this probability. Notice that B2 over B4, 0.25 over zero point 0.5 is zero point 0.5. So what I am in effect doing is I'm scaling up these two probabilities, 0.25 and 0.25, so that they will actually add up to 1. So that's the first case when x is 1. Then when y is minus 1. Y can also be plus 1. I do the probability. I scale it up with this one, so it's a total of probability 1. So this is the expected value of y when x is minus 1. That makes sense, right? Because if x is minus 1, there is a 50-50 chance that y is minus 1 and plus 1. And the expected value of minus 1 and plus 1 in a 50-50 case is 0. We can do exactly the same thing for x is equal to 1. So now we can do minus 1, that's the first possible case, multiply by this probability. Now we know that x is 1. Scale it up with this one, plus, y can take the value plus 1, multiply by the probability, which is scaled like that. So we see that the expected value of y given x equal to 1 is this number 0. There are probabilities involved in this case as well, because x can take the value minus 1, and the probability of that is just this one right here, 50% chance, and the probability that x is equal to plus 1 is this probability here. So this is in the sense that the expected value of y given x is a random variable. It's a random variable that can take value 0 with 50% probability, and it takes value 0 with 50% probability. So in this case, kind of a boring random variable, it takes value 0 with 100% probability. But we should expect that, because in this case, there's no covariance between them. And for this particular case, it means that there is absolutely no relationship between them either. So the expected value of y given x should be the same as the expected value of y, which is 0. But we can easily make this a little bit more interesting. So remember, if we took this up to 0.3 on the diagonal and took it to 0.2 on the off diagonal, then we have a much more interesting case. First of all, remember, that gave us a positive covariance. And now the expected value of y given x is no longer 0. The expected value of y conditionally on x is minus 1 is now negative. Why? Well, because of the positive covariance. If you condition on x being minus 1, then y can take values minus 1 and plus 1. And you can see that it's a larger probability that it takes the value minus 1. It makes sense since they're positively correlated. So smaller probability that it takes a value which is of plus 1. And that's why the expected value of y given x minus 1 is negative. In exactly the same kind of argument, the expected value of y when x is plus 1 must be positive, because now we're focusing on these two possible outcomes. You can try yourself with the opposite, putting 0.3 on the off diagonal and 0.2 on the diagonal elements. That will make the covariance negative, and that will make the expected value of y given x minus 1 positive, and it will make this one negative. But the important part to note here is that if I know the value of x, the expected value of y given x is just this number. If I don't know the value of x, that is, it can be this or it could be that, you have to view expected value of y given x as a random variable. A random variable that comes out to this number if x is minus 1 and this number if x is plus 1 with these two probabilities. That in turn means that this conditional expectation in turn has an expected value. So I can calculate the expected value of this conditional expectation. And that's pretty straightforward. We know how to do that. Just take the outcome, multiply by the probability, add the second outcome, multiply by its probability. And we see that the expected value of the conditional expectation is 0. And there is a famous result in probability theory saying that this expected value, let's put it here, expected value of the conditional expectation, like this, is always equal to the unconditional expectation. That's called the Law of Iterated Expectations. So if we paint this yellow, then no matter how you change these probabilities, these will always be the same. So you can do something which is not symmetric, let's say 0.2, 0.1, 0.3, how much have I left? 5, 6, and 0.4. Covariance came out to be 0.2. The expected value of y is 0.4. The weighted average of minus 1 and 1 with these two weights, clearly that's positive. The conditional expectation is this random variable, 0.2 with probability 50%, 0.6 with probability 50%. And if you take the expected value of that, you get 0.4, exactly the same numbers here.